All right, let's go and get started. All right, let's go ahead and settle down. All right, couple things. All right. All right, so a couple things. Number one, you all have homework 3 due on Friday, February 10th. That's this Friday. The homework is, I think some of you have already started the homework, and I think those of you that have started it have probably seen that it's really short. It's a really short assignment. A couple of things. I had a student bring this up to me, and I've got to say that the amazing eye, because I didn't see this, but if you look at problem 3.9, yeah, I didn't even notice that. So if you look at problem 3.9, the diagram states, and it writes out 6 number 11 bars, but it literally has 7 circles. So I was like, wow, I didn't even see that. So, but just go with the label. So 6 number 11 bars. I mean, when we're, I will say this, in our design calcs that we're doing later, we're just assuming like a layer. So it doesn't really matter how many bars, and then we'll populate it with steel later. So for the assignment, just assume 6 number 11s, just go with the label. But yeah, that was a great eye. I didn't even see that. One other thing I'll point out, on the assignment, I indicated that I wanted you all to determine whether or not the beam meets minimum steel requirements. And I'm talking about this on slide 94, which is just ensuring that the beam has enough steel to prevent premature failure. And that should be more than enough. So, or the beam should have more than enough. But there's the limit on that. Does anybody else have any other questions on homework 3? Again, this should be a really short assignment. I just wanted a quick assignment to go through some of the details that might be, I don't want to say a little cloudy, but I just wanted everybody to sort of go through them once before we get our big design homework, which will be assigned afterwards. Yes, sir. Well, okay. I'll say this. You're asking sort of a really loaded question, but I'll say a couple things. Number one, I mean, if you're in design mode, I mean, like, for instance, the example that we did in class, I mean, it said simply supported. So just go off of that. As for, in a larger context, whether or not we're talking about a building or a bridge or something like that, if we're talking about a building, it just depends on what the architect needs. I mean, does the architect need a cantilevered beam, or do they need a simply supported beam? Does the beam layout need multiple supports? Does it need a fixed end? Does it need a simple support? It's just dependent upon the problem. So yeah. Does that answer your question? I don't really have a clear-cut, better answer other than it's based on the constraints of the design. So, sound good? Anybody else? Yes, sir. What do you mean? Simple beams are simple. No, in all seriousness, I mean, I would do my best to just keep designs as simple as possible. I mean, when we took structural analysis, I mean, I'm not going to lie, I was giving you some beams that, you know, in terms of reality, probably were a little stupid. I mean, you've got beams with hinges and triangular loads and all this weird stuff. The point is, if you can do that, you can certainly do the analysis that we do in here. And by and large, most engineers are going to do their damnedest to keep the project as simple as possible. So, you know, take beams. Like a simply supported beam with a uniformly distributed load, hell, that'll get you 80–90% of the beams you'll design throughout your whole career, you know. Every now and then you're going to have one that's a little strange. You just need to be able to handle it. So, but yeah, I do my best to keep it simple. So, complications are just that, complications. Anybody else? This is good stuff. All right. So, SAME ASC meeting tomorrow at 6 o'clock in 2241, right over here, just upstairs across the hall. Exam 1, I started doing this in steel, so I figured go ahead and start doing it in concrete so that nobody is surprised when the exam date shows up. It's going to be Wednesday, February 22nd. One final note, I am currently passing around the binder. I don't know where it's at. There you go. Go through the binder. If you're missing anything, let me know. Put it on the attendance sheet, and I'll come out with some printouts. But again, everything's on Blackboard, so you should have everything that you need. But I'll bring out printouts. Sound good? All right. Let's get back into some design. We were really sort of trucking along last time, and I want to continue on with that today. So let me go back to our design example. Let's be clear. Let's just sort of bring it back so that everybody's aware of what we were doing for our design example for example 6. Because remember, this is one where we didn't have a clue what the beam looks like. It was an unknown cross-section design. It was 22 foot long. It was simply supported. It had a kip per foot in dead load in addition to the self-weight. And then it had 2 kips per foot live load, but that was already reduced. We had 4 KSI concrete, 60 KSI steel. We have normal weight concrete, and we went with a D over B ratio of 1.5. Now let's sort of go through our calcs, and let's keep on trucking with this to sort of finish out our design. Now, I want to point out a couple things. So this was our example. This is where we were started. Now, at the very beginning, we didn't have a clue what the self-weight of the beam was at all because we were in design mode, right? So we did some pretty basic calcs, and we said, well, let's just assume right off the bat that the beam's about 16.5 inches tall. Now, for our trial design, is it 16.5 inches tall? Anybody remember how tall our trial section was? That's the base. I want to know how tall the beam is. 24, all right, right there. We assumed a self-weight at the very beginning, and we assumed a self-weight based on a height of 16.5 inches. But when we went and did our calcs, we got a height of what? 24. Oh, so now the beam is heavier than what we assumed. So we got to go back and check that assumption. You see what I mean? So these are the assumptions that we made that, if we don't go back and validate those assumptions, they're pretty meaningless. So we have to go back and update our beam self-weight and go through and do all that again. So let's continue and walk through our calcs. So we calculated our beam self-weight, which is gamma times BH. We got our factored load, 1.2 dead plus 1.6 live. Remember, we added up our superimposed loads. And then did our moment, which it is a simply supported beam. It is uniformly distributed loading, so it's just WL squared over 8. That's pretty simple. Next thing we did, we said, all right, let's divide by phi, and that's another assumption. Phi's 0.9. We guess. We would love it to be 0.9, but that's a guess. We're going to have to go back and check that. Okay. Next thing, we calculated a rho value for design purposes. If you have no other place to start or no other indication on your design, go with 0.18 FC prime over FY. It's a rule of thumb, but it works very well. Once you've got that, you can compute your required BD squared. I know the formula is a little involved, but ultimately it's plug and chug. And you get about 5,700 cubic inches. You can take that and ultimately start coming up with some required beam dimensions. So we went off of a B over D ratio of 1.5, so that indicated that the beam needed to be about 13.7 inches wide, so keep it simple. We said, let's just take that to 14, make our beam depth, our effective depth, 1.5 times that, which is 21, add another 3 inches for cover and reinforcement requirements. So here's the dimensions of our beam. It's a trial section, but at least it gets us started. Everybody okay up until there? Okay. Now our required AS, rho BD, so go ahead and say, all right, rho, the 0.18 FC prime over FY times B times D, that gave us a target for our steel reinforcement, and now we're starting to select patterns of reinforcement. So we did a couple of these. Let's do some more. So let's just sort of walk through how we did this. So we started off, we said, okay, let's do number 6 bars. We said, how many number 6 bars must we select in order to meet a steel requirement of 3.528? We said, well, 8 bars will do it because that'll give us an area of 3.53. So let's see if that works. Well, if we then go to the table below and we say, well, how wide does that beam need to be in order to fit 8 number 6 bars in it? Well, it needs to be about 17.5 inches wide. That's no good because the beam's only 14 inches wide. We just don't have the space. Okay? So let's kick that one off. Let's do number 7s. We said, well, how many number 7 bars do we need? We'll go through the table. We find, oh, well, we can do it with 6 of them. That'll be an area of 3.61. Remember, that's our target, so we're good there. Will that work? Well, nope, because check the beam width on the bottom. We only got about 14.7, or we only got about 14 inches, and we need 14.7. So that option isn't any good either. So the next natural assumption is, okay, let's try number 8s. Now, you could also have gone to number 5s and number 4s, but that would have been the same story. It would have been more and more bars, and you'd have needed more and more space. So help me out. How many number 8 bars can we use to meet this requirement? I heard somebody say something. 5. Okay, so if we select 5 number 8 bars, bless you, how much steel does that give us? Now, that's a valid assumption, but can we fit it? How much space do we need for 5 number 8s? 13.3? Is that a viable option? There we go. So there's one. That one works. We're not done, though. We're not done. Let's keep going. You'll see why. Let's do number 9s. How many number 9s? Somebody else. Somebody over here. How many number 9s? You 4? There we go. Bless you. Now, if I pick 4 number 9s, how much steel does that give me? And how wide does my beam need to be? What? 12.1. So is that good? Now, before I move on, is everybody else able to follow along with me on this? Does anybody have any questions about how I'm doing this? Okay. All right. Somebody over here. Mr. Foreman. How many number 10s? Two? All right. If I pick 2 number 10s, what's my area? There we go. All right. So what is my area if I pick 3 number 10s? There's a reason why I'm writing all these areas down. So say it again. No. I need the area, though. 3.79, and then this one's 10.4, right? There we go. So is this last one a viable option? Okay. Now, let's just leave these on the screen right now, and then let's assess them. Okay? Now, let me ask you, how many viable options do I have? 3. Now, top, middle, bottom. Which one should I go with? Well, that's what this is telling us.
Well, I mean, would you want, because the minimum width on that one is like number 8 is 13.3 inches. If your width is 14, it does you a very small little bit of cover.
Keep in mind, this minimum width is already accounting for it's already accounting for it. So you've met that, and you've got a little bit more room to work with. Now, somebody mentioned the cheapest. Okay, so let's think about it like this. Cheapest, by and large, tends to refer to pounds of steel. All right? So which option is going to result in fewest or smallest number of pounds of steel? The number 10s, right? And how do you know that? Smallest area. That's why I was writing those areas down, right? So between the top, the middle, and the bottom one, go with that one. Okay? Yes, sir? Because look, we went. This one was larger, but that one wasn't. See what I mean? Okay, you're exactly right. Let's keep going. Okay, let's keep going. All right? No. Oh, yes, you were. Yes, you were. Now, hold on. First off, I'm going to box this one. No. This is important. This really is, okay? All right. Now, how many, what's the next bar? Number 11? How many number 11s would we need? And how big is that? So that one doesn't work. What about number 14s? That ain't going to work, is it? What about number 18s? All right. Now, what about, so we can't, I mean, everything past that is just going to give us a larger answer, right? So let me sort of expand on Mr. Schaffer's point. You just need to go through and check them all, okay? Now, I stopped here because I think by now you all have kind of gotten the visual point of how to assess the table. And you can just look at this option and say, well, everything past that is just larger and larger amounts of steel. We have a viable option. Based on this range, it's the most economical. And we just look and see that for the rest of them, it's the case as well. So that's the option I'm going to go with, okay? Does that make sense? And does that answer your, I mean, that was a good point. That was a really good point. All right? Everybody else okay with this? Yes, sir. More often than not, yeah. But let me also state, I am aware that we only have 50 minutes, so I have my ways of crunching the problems down a little bit. So. I don't know about what? Who's what? What? Who's? I don't know. So let me. All right. Does everybody have this? Everybody have this? Okay. All right. I'm gonna go on. So I propose then that, for example, 6. All right. My trial beam, or my trial design, beam design, looks like this. All right? All right? And then we've got 3 bars. I'm actually going to draw 3 circles. I'm not going to mess that up like the book did. So this is 3 number 10s, and that is an area of steel of 3.79. This dimension is 21 inches. This dimension is 24 inches. This dimension is 14. There's my design right there. We know how big the beam is. We know how deep the beam is. We know the number of bars. We know the area. There's my design. This design, however, is a trial design. I still don't know if this design is going to work because I made some assumptions when I developed this. Yes, sir.
Yeah. Do we include the stirrups in the?
Yeah, okay, that's a good question. So if you want, you can put your stirrup down and say, okay, I've got, and I just break that up with the text, but I've got stirrups in there as well. We are later on going to determine how to space those stirrups out. That's for shear, and that comes later.
Yeah. My question was related to this. So if we include the stirrups, do we include 3 bars at the?
You mean up here?
Top, yeah.
That's a great question as well. The answer is, for now, we're just going to neglect it. You can account for that reinforcement up top. What we would be dealing with then is what's called a doubly reinforced beam. A doubly reinforced beam we consider the reinforcement in the compression region as well. You can handle it. We will discuss how to do that later. By and large, it's really better just for an analysis perspective. If you include it, you can get a little bit of a benefit in your capacity. Also, compression steel helps with long-term deflections, and we'll talk about that later. But you can't account for it. For now, I'm not, but you can't account for it. Yeah, but not appreciably. I mean, remember, we're not using, when we use 150 pounds per cubic foot, I mean, really, normal weight concrete's about 145. We're using 150 to account for the normal weight of reinforced concrete. By using that weight of 150, we're accounting for that, a little bit of a bump up in unit weight to account for reinforcement. I mean, I'm sure if I threw one more bar in there that, yeah, it's going to get a little bit heavier, but using 150 is close enough for government work, and that's why we use it. So that's a good point. What's that? I'm just, well, I guess I work for the government too. So I work for the state of West Virginia. So. All right. I like my job. I like my job. All right. Has everybody got this? All right. This is a trial beam design. We have to validate our assumptions. So the easiest way to do that is to just analyze the section. So step 9, analyze trial beam. So when I say analyze trial beam, we're going to have to determine factored moments and factored resistance. So let's start off with factored moments. Now we know the dead load and we know the live load, but we now have a new self-weight that we need to compute because the beam is heavier. So we say, all right, W sub naught is gamma BH, which is, how heavy is the concrete? We just talked about it. So 150 pounds per cubic foot, or, there we go, 0.15 kips. Width is, how wide is the beam? There we go. And how tall? Not 21. It's actually 24. Now we've got, there we go. What am I missing? And what is my conversion factor? There we go. So now, does that look better? Got y'all paying attention? That's what I like to see. Somebody back here, tell me what we got. Don't even have the calculator unsleeved. See, hold on. Just, where's your calculator?
It's in my head.
It's in your what?
It's in my head.
Missing in academia?
Yeah.
What do we got? 0.375. I got a second on that? That's what I got 0.35. You have 0.15 times 14 times 24? What do we have? There we go. Now, what did we initially assume? What was our unit weight that we calculated before? Say it again. So this is heavier than we assumed. And that's okay, because we're checking it now. All right. So there's that. What is our dead and live load? Let's see if y'all remember. And what? And the other one, somebody else over here.
2.
There we go. So if I got dead loads and live loads, what do? There we go. Remember, the self-weight and the superimposed dead load are just that. They're all dead loads, so lump them all together. so 1.2 dead plus 1.6 live, so 1.2. What do we get? 4.82. Do I got a second on that? Now what? You tell me. We got a factored load. What do we do with it? There we go. And how do we calculate that? There we go. How long's the beam? There we go. Help me out. What is M sub U? That was a good one. Say it again. 291.6. Now, what are the units? There we go. Got a second on that? All right. Now, here's what I'm going to do. I'm going to take, this is a really important value, so I'm going to underline that because that is the factored moment. All right. We are going to compare that to phi mn factored resistance. So factored load compared to factored resistance. All right. Does everybody have this? Everybody good? All right. All right. Now, this is a long example, I know, but it's a start to finish beam design, so it's going to take us a little while. All right. Now, we have got a single reinforced concrete beam. We know its dimensions, we know the rebar, we know all of that. So help me out. How do we determine its resistance? In other words, we need to determine phi mn. Okay, so let's take the phi off the table. Let's just do mn. How do we determine mn? What's the first step in getting mn? All right, so yeah, our force times our distance. Now, let's just go back. Remember when we determine our nominal resistance, you're onto it, so.
It's the nominal moment, right?
Yes.
The design moment.
Well, yeah. The phi mn.
So it's the previous value we just had.
No. That's the load.
Oh.
Where I'm after is the strength, how strong the beam is. Okay, ASFY D minus A over 2. Remember that? What don't we know? Say it again. We don't know A, right? Does anybody remember how we computed A? There you go. We used the concept to start off that C equals T. Y'all remember this? So what is the compressive force in the concrete? How do we compute that? There we go. Remember that? Now, how do we compute the tensile force in the steel? There you go. Does everybody remember this? All right. So how do we solve for A? What is A? It's a fraction, right? Now help me out. You tell me what to write. What is the area of steel? Remember, none of the design values. We now have a beam that we're analyzing. So, Mr. Crookshanks, what's the area of steel? No. No. The 3.79, right? Now, all right, Mr. Crookshanks, I'm going to give you another. What is Fy? No, hold on. This is 3.79 square inches. What's Fy? Remember that we got 4 KSI concrete. What's going on with the steel? Yeah, so 60 KSI. So 0.85. FC prime, what's FC prime? And B, what's B? 14. Does everybody know where I'm getting these? Well, that, and not just that, though, the actual beam, the trial beam. Because, like, the area of the steel, the beam width, I mean, yeah. So what do we got here for A? 4.78. I got a second on that? Now, how do I compute the nominal moment capacity? Now tell me what to do. We've been talking about it earlier, so. Yep. And what was that? There we go. Remember, just a force times a moment arm. The D minus A over 2, that's that distance from the C and T. All right? Now help me out. AS is, there we go. FY is, all right. What is D? 21 inches. There you go. Not 24. Minus, what does that come out to be? First off, what units is it going to come out to be in? It's a moment. There you go. So when it's all said and done, we're going to take this number and do what to it? Multiply or divide. There we go. All right, so 3.79 times all, you tell me what you got. 4231 point what? I think that was seconded. So what is that in foot kips? So 7. We'll keep it simple. All right. Everybody with me so far? That's nominal resistance. That's Mn. We don't really care about Mn. We care about phi Mn. So to calculate phi, what are we going to need to determine? No, that's rho. No, that's rho. We're going to need beta sub 1, but ultimately phi is based off of what in the steel. There's something going on in the steel. The strain. We need the strain in the steel, right? There you go. Yeah. So first off, let's keep it simple. So strength reduction factor. First thing we're going to need is beta 1. What is beta 1 for 4 KSI concrete? 0.85. Does everybody see that? So if I've got beta 1, what can I do with that? I can find C, right? We've got C. It's just going to be A over beta 1. So 4.78 over 0.85, what does that come out to be? You said 5.63? 62. Do I have a second on that? Now, anybody remember how to compute the strain in the steel? go off in similar triangles. There you go. Exactly right. So the strain in the steel, or the strain in the tensile region, is 0.003 D minus C over C. Remember, we're just using similar triangles, and we're assuming that the strain up top in the concrete is 0.003. So 0.003 is to C as whatever this is to D minus C. It's just a ratio. So plug and chug. And what do we got? We've got 0.003 times D is what again? There we go. Keeping y'all on your toes. And then 5.62. 5.62. Now, what does that come out to be? Times 10 to the negative third. So let me see. Do I have 0.0082? Is that a fair point? All right. What observations can we make about that based on that value? Okay, all right. Two things. You both have sort of hit on two things. So number one, it's greater than 0.004, which means it meets ACI requirements. So that's good. So we'll say epsilon sub t is greater than 0.004. So that means the design is okay. It's got to be greater than 0.004 regardless. Yes, sir. That comes from ACI spec. That was, yes. All right. That's point one. Now, what you were saying, you continue on with your thought.
So off of that chart that we have, greater than 0.004, p-value.
Not 004, 005.
0.05, sorry.
Yeah.
Then the p-value is 0.9.
There you go. So just so everybody's clear on that, let me go back to the PowerPoint because I don't want there to be any ambiguity on this. Has everybody got this written down? Oh, well, here, I'm going to come back to it. So, let's see. Right here. So, first off, according to ACI, no matter what, our strain's got to be greater than 0.004. That's just, I don't care what's going on. That's just to enforce that whatever design we use, the tensile reinforcement in a beam has to yield. Okay? That's point one. Point two is this. Remember, this is the curve that we use to determine our strength reduction factor. If our strain is larger than 0.005, then it's always 0.9. Otherwise, we just use this linear interpolation right here, which that's what you all are doing on homework 3. That's the whole point, is to go through all these details that all, you know, I just showed them to you. Now I want you to practice them. That's what homework 3 is about. It's the minimum steel, the strain, all that. So is everybody okay with how I'm saying phi is 0.9? That's a valid assumption, right? We assumed that before and we got a right value, so that's good. All right, so what I'm then going to say is this. My factored resistance, so phi mn is going to be phi. What is phi? 0.9. And let's see, factored resistance. Let's see, somebody back. Mr. Lyman, what we got? What's my factored resistance? 352.7. All right, so what do we got when we chug this out? 317.43. I got a second on that? Well, then, if I do this. All right. what does that value mean? I mean, what do I compare that to? MU, right? What was MU? What was our factored moment? That's good, right? That means our design is, in fact, safe. Now, how do we determine how efficient our design is? Yeah, we calculate the efficiency, mu over phi mn. So, first off, our design is okay. Our efficiency is mu over phi mn, which is what? So we've got mu is 291.6, and then phi mn is 317.4. 0.92, so in percentage, maybe something like that. Tell me what that means. Is that a good design? That's a good design. What if that value was over 100%? What would that mean? That was a bad design, right? Now, I'm just curious. I'm just curious. Let's say we had a bad design. Let's say those assumptions didn't work out. Help me out. What can I do to the beam that I got? Remember, here's the beam I got. All right, it's 14 inches wide, 21 inches in effective depth, 24 inches tall total. It's got 3 number 10s in it. 4 KSI concrete, 6 KSI steel. What can I do to that beam to make it stronger? Help me out. What's that? Say it again.
Increase the depth.
Okay, increase the depth. That's one of them. All right. Now let me just say this: if we could increase the depth, I'd love to do it. Ultimately, it's going to result in a massive amount of capacity, but maybe we don't have room. So ultimately, add more reinforcement. Okay, so that's point 2. You could add more reinforcement. Maybe use that number 8 option or the number 9 option. We know that'll work. That's an easy one, actually. That's a really easy one. Just go with that number 8 option or that number 9 option. That's another one. Maybe make it 70 KSI bars or 80 KSI bars. Maybe another one, make it 5 KSI concrete, 6 KSI concrete. What's another one? Yes, sir.
Your efficiency is over 100%. Does that mean you're
No,
over
that's the opposite. That means you have more load than you do resistance. That's bad. That's grandma's in the river. No, seriously, that's what that means. That means the element is going to fail. So, considering uncertainty and all that. What's another one? Increase the beam width. That's another one. By and large, I'll say that what will give you the most bang for your buck in upping the capacity is Mr. Cruikshank's suggestion. Just up the steel. Okay. You can't go too much, but you can up it a little bit. There's also some larger scale issues that you can do in design. What if this beam is part of a series of beams in a bay in a building? Maybe add more beams. You add more beams, each beam gets smaller. You see what I mean? Or the demand on each beam gets smaller. Now, it's an economic trade-off. More beams means more to construct. So it's trade-off. Yes, sir. Well, that was one of the suggestions we mentioned earlier, is that maybe change the rebar grade or the concrete grade. I will say this. You would be surprised if you actually go through and do the math how little concrete compressive strength actually affects the capacity. In other words, if I did all that math but did it with 5 KSI concrete, you'd be surprised how little that value actually goes up. I mean, it will increase, but not as much as you would think. It matters, but not a lot. Okay? Any other questions? This is good stuff. All right, we have one more thing we got to do, and it, by and large, will never govern, but we still got to do it. Everybody have this? All right, we have to check our minimum steel. So All right, so we have AS min is BW, which is just the beam width, times the depth, over FY, times the maximum of 3 square root of FC prime, or 200 PSI. All right, so over here on off to the side, I'm going to compute 3 square root of FC prime, so 3 square root of what? There you go, 4,000. You put in PSI, you get out PSI, anytime you do a square root. So square root of 4,000 PSI, so what is that? 189.7. So, which is larger, that or 200? 200, yeah. So all we've got is BWD times 200 PSI over FY. So what is BW? That's just the beam width, which is 14 inches. D is 21 inches times 200 PSI. Oh, I can do better than that. Over FY, which is 60,000. Exactly. Units matter. Units matter. 60,000 PSI. Which, what does that come out to be? 0.98. Do I got a second on that? All right. Okay, so 0.98 square inches. Are we good? Yeah, we provided, what, 3.79? We're good. By and large, this limit should never really govern. You still need to do it, though, okay? So, therefore, I mean, this is what I'm going to do, all right? I'm going to write out a design summary. Okay? So here's my design summary, all right? Phi Mn was what? 317.4 foot kits. Now what was Mu? Now based off of these two values, we calculated an efficiency that was roughly, what'd you say, Mr. Kirschink, 92? 92%. So that's pretty good. All right? There's two other limits that we needed to check. Our strain in our steel was greater than 0.004. We did do that. We had one more, our area. And our area was greater than the minimum. So what is the answer? Here's the answer. There's your answer right there. And that is your answer based off of this right here. We have a factored resistance that is greater than or equal to the loads that it's being subjected to with an efficiency over 90%. We have, bless you, we have a strain in our steel that is greater than what is required by ACI, and we have provided an amount of steel greater than what is required. There's your answer right there. There's your design. So just take a moment and take it all in.
You've already done that.
No, but this is the one you really need to take it in. Okay, all right. Does anybody have any questions about this? I do have something I want to show you all real quick before we leave. Okay, look, let me show you something real quick, all right? Now, so what we just did, was the design of a beam with an unknown cross-section. We had no clue whatsoever what the beam would look like at the very beginning, and then we arrived at a design. That's an unknown cross-section design. Next, we're going to do a known cross-section design. We know what the beam looks like, and all we need to do is select rebar. Now, here's where you got to pay attention. We used a rho value at the very beginning of what? What was like 0.18 FC prime over Fy? That is a good value when you don't have a clue at square one. You don't have any clue what the beam looks like. Here, this is a different story. We know what the beam looks like. And when you know what the beam looks like, you can actually solve for what your rho is. So this is very important. On unknown cross-section designs, we just say at 0.18 FC prime over Fy, that'll get us started. But when you know what the beam looks like, no, you can solve for it, okay? So when you know what the beam looks like, you can solve for it. We'll discuss that math, and we have the derivation of that next time. We'll go into that, and then we'll get into our known cross-section. I will say the design of a known cross-section beam is a lot easier because there's a lot less steps. You know what the beam looks like. You don't have to iterate the self-weight because you got the beam. It's right there. So you just have to calculate it and move on. So, all right. Sound good? That's all I got. I will see you all on Wednesday.